In this video, I want to talk about the relationship between equivalence relations and partitions. Let's start by assuming we have some partition of a set A, the partition denoted by A sub I. I want to be able to define an equivalence relation on this partition. I'm going to define this by saying X is equivalent to Y if and only if X and Y are in the same class of the partition. So if they're in the same set A sub I, then we call them equivalent. So I want to show this as an equivalence relation. The first thing I need to show is the reflexive property. We know that X is equivalent to X since X is in the same class as itself. So that gives us the reflexive property. Next, we need symmetry. We know that if X and Y are in the same class, then Y and X are in the same class. So that gives me the symmetry relation. Finally, the transitive property. If X and Y are in the same class and Y and Z are in the same class, then we know that X and Z must be in the same class. So if we define X equivalent to Y by being in the same class of the partition, then we can get an equivalence relation from this partition. So every partition has a related equivalence relation. Next, let's do a little bit of notation. We'll let tilde be an equivalence relation on A, and we'll let X be some element of this set A. We say the set of all elements equivalent to X. That's called the equivalence class of X, and it's denoted by this X with square brackets. So in symbols, X in square brackets is the set of all Y belonging to my set A such that Y is equivalent to X. So this is known as the equivalence class of our equivalence relation. A useful property of equivalence classes is that if X is equivalent to Y, then the equivalence class of X is the same as the equivalence class of Y. So if two elements are equivalent, they have the same equivalence class. And this should be fairly obvious. If X is equivalent to Y, then the elements equivalent to X are the same as the elements equivalent to Y, using a combination of symmetry and transitive properties. The next big result, if tilde is an equivalence relation on A, then the family of all equivalence classes, that is the set of all equivalence classes X, such that X is in A, is a partition of A. And this is a big result. I already discussed previously in this video how every partition gives rise to an equivalence relation, and now I'm saying every equivalence relation also gives rise to a partition. So we can use equivalence relations and partitions interchangeably. So let's show this is a partition. For a partition, we need three things. First, we need these sets to be non-empty. We need non-empty sets. Well, since this is an equivalence relation, we know X is equivalent to X. So at the very least, X is in the equivalence class of X. So these are non-empty sets. We also need them to be disjoint. Let's pick an element U that's in the equivalence class generated by X as well as the equivalence class of Y. Well, since U is in the equivalence class for X, we know that U is equivalent to X. Since it's in the equivalence class for Y, we know that U is equivalent to Y. Using symmetry in the transitive property, we then have X is equivalent to Y. And we just discussed how if two things were equivalent, then their equivalence classes were the same. So this shows that they are disjoint. The last thing we need to show is that the union of all of these is equal to all of A. So if I take a random element of A, I need to be able to definitely say it belongs to a particular equivalence class. Well, that's pretty easy to see since X is in its own equivalence class. So I've done enough to show that this is in fact a partition of A. So now that I have that, I can use this idea of equivalence relations and this idea of partitions very interchangeably, since every equivalence relation gives rise to a partition, and every partition gives rise to an equivalence relation.